Okay, so this is a picture of an overhead projector. Um, it's just got a sheet of paper laying over it, and I'm going to talk about some polarizing filters. So this is a polarizer, and you have glasses made out of these. They're used in a wide sunglasses sometimes made out of these. And basically, we talked about light being a combination of perpendicular electric and magnetic fields oscillating. Well, this strips out only the electric fields going along a certain direction, the grain of the polarizer. And so it cuts out approximately half the intensity of the light. All the components that are perpendicular to that get wiped out. And so you can kind of see that when I put that polarizer on there, it cuts out a bunch of the light that the sheet of paper is letting through. And now I'm going to take a second one, and it's identical to the first one, but it's called the analyzer, because as I bring it in, you can kind of see that if I turn it a certain way, it doesn't seem to make the thing much darker, right? Just a little bit. But if I rotate it, it completely blacks out the image behind. And that's because if the grains are lined up, then the light that gets through one will get through the other. But if I rotate this one so that the grains are perpendicular to each other, then none of the light gets through. The stuff that gets through the first one is now perpendicular to the grain of the second one, and so it doesn't get through. And so that's how polarizers work. It turns out that light that's reflected off surfaces, and I'll show you this in a few minutes, like the ground and stuff, is preferentially polarized in that plane. So sunlight that bounces off wet pavement in front of you is generally polarized along the plane of the pavement. And so if you have sunglasses that are perpendicular to that have a grain perpendicular to that, then those glasses will block out the glare off that reflected sunlight. And so that's why sunglasses are often made from polarizing materials rather than just darkening materials. So this was so these are two pieces of polarizing film. And so I have a few more demonstrations. So this is a clear box that's got polarizer on one side and analyzer on the other. It's actually, I mean, they're the same thing, but if you notice that they're oriented 90 degrees to each other, and it's got a compartment, and I'm going to be able to stick stuff in the compartment. So if I set this down like this, you'll see. Oh, sorry. You'll see that. Let me use another sheet here so I can block off all the backlight. Like that, maybe. Is that better? That's a little better. So now you're looking through two sheets, and it's mostly darkened. But now I can take like one of these polarizing sheets and slide it inside, and you'll see that if I turn it the right way, I can actually get some light to come through, because if the grain of this one is at 45 degrees to the bottom one, and thus also 45 degrees to the top one, I'm now letting some light through. If it's parallel to either one, then I let no light through. And so anything in between that rotates the polarization of the light, anything between these two, the top and the bottom surface, will cause some of the light to get through. I need to do a smaller rotation for this one to get to the bright spots. And so another interesting aspect of this is I can take here's just a piece of plastic that's shaped like a tuning fork or something, and I'm going to slide it in there, and you're going to see it doesn't do much, but then I'm going to squeeze it, and you'll see that as I squeeze it, it's doing something to the polarization of the light in between the two polarizing and analyzing surfaces. And that's because plastics tend to do that. Plastics under stress tend to change the polarization of light that's passing through them. And so this is a demonstration of that. Often they will make, I don't know if they do this anymore, but they used to maybe make a bridge or a building, a model of one. So if they were going to make one, they'd make a scale version of that and out of plastic, and then look at it through polarized light, and they could see where the strains were in the bridge or the building to tell what the stresses were on the building. Here's just a plastic tape dispenser if I throw it in there, you'll see that it does some weird things to the light going through it. You can see some colors in there and stuff. So this thing is changing the polarization of different colors of light differently. It's having a different effect on different colors, right? The white light that comes through is all different colors, and you're seeing how the rotation of the polarization of different colors of light is affected. Here's a glass cube, right? And this is also under various crazy stresses. If I stick it in here, you'll kind of see it, right? And I can take it and rotate it different ways, put it on a different axis or something like that. And you can see it's got colors in it and does crazy things to the polarization of the light going through it. Here's just another one of the same thing, but it'll have slightly different probably. Yeah, slightly different effect. It's under slightly different stresses. Glass is cool, and they're made melted, and so when they cool, they develop different stresses depending on the individual piece of glass. I don't know if I have many more of these things. This might be one. This is a prism. Not much effect there. Here's another just little plastic container. Once again, you see crazy things from it as the light goes through it. All right, so that's a little bit about polarization. So what you're looking at there, I'll just scan down a little bit, is a reflection of the light, right? Those lights off the table in front of you, right? And so that's just a reflection of the light off a lab table. And what I want you to see is that the light that comes through there, right, is polarized. So now I've put a polarizer in front of the light, in front of the camera, and now watch what happens when I rotate it. Right now, none of the light gets through, or almost none of the light gets through. Part of that just depends on the angle, which we'll talk about in a little bit. When light reflects off a surface, as I said earlier, it's polarized, preferentially polarized in the plane of the surface. It has to be reflected at a certain angle to be 100% polarized in that plane, but it looks like I'm pretty close to that right now. And so you can see almost all of the light goes away when I orient the polarizing disk in a certain way. Right. So the last section is on polarization. We already said that light is composed of oscillating electric and magnetic fields. And we might say the electric field is oscillating this way, and the magnetic field is oscillating into and out of the. So while the electric field is going up and down, the magnetic field is going in and out like that, something like that. And so we define the direction of polarization as the direction of the electric field. And so we can have a light that's coming off a light source. So if I have a light bulb here, right, that's producing light, we say the light is coming out with all polarization. So, these might be drawings. The light's traveling this way. It's traveling in all directions, but we'll say it's going that way. The light's going that way. Some of it's polarized like this, some is polarized like this, some, like this, all the way around. So the electric fields are oscillating in all directions. What a polarizer does, a polarizer is a disk or some film that the light has to travel through. And that disk only lets light through that has that's aligned along the axis of the polarizer. And so in this case, I've drawn it up and down. And so now the light that comes out of here is all polarized like this. And so what we say is if the intensity of light here is I0, the intensity here is I1, and that's equal to I0 over 2. You may say, well, if the intensity, if you're stripping out only the ones that are up and down, surely that's not just half of them. It would be a much smaller fraction. Well, what the polarizer does is if there's a ray that's polarized like this, it just takes the vertical component of that. And so part of it's polarized horizontally relative to this, and part of it's polarized vertically. And so it strips out all the vertical components of all of these rays, and then lets those through. And so then you get light that's only vertically polarized. And then you can put on here, you can put an analyzer, and we've already shown in the little demo, if you've looked at that, that if the analyzer goes like this, then we can say I2 equals 0, because these two make a 90-degree angle to each other, right? If, however, instead the analyzer, which I'm going to draw as a disk, these are supposed to be, disks like this, right? Except it lets light through. I'll get one in a second. Now we're going to say that just in general, the analyzer makes an angle theta. So here's the perpendicular, right? This angle is theta, right? So the axis of the analyzer and the axis of the polarizer make an angle theta. And if that's the case, then I2 is equal to I1 cosine squared of theta. Right? If theta is 90 degrees, cosine of 90 degrees is 0, I2 is 0. Right? And so this would be right. So compared to the original intensity, the intensity that makes it all the way through the analyzer is I1, or I0 over 2, times cosine squared of this angle. If this angle is 0, then all the light that got through this guy got through this guy, because he was lined up vertically, and that's what we saw in the little demo. If this guy's 90 degrees, it's 0. If this guy's somewhere in between, it's somewhere in between. And so we can ask the question, so we say how much light gets through the analyzer if its axis, if theta is 30 degrees. And so I can just solve this down here. I can say, well, look, I2 is equal to I1 cosine squared theta, which is I0 over 2, right? Cosine squared theta, which is I0 over 2 cosine squared of 30 degrees, right? Which is I0 over 2. Cosine of 30 degrees is the square root of 3 over 2. So square root of 3 over 2 squared. Square root of 3 squared is 3. 2 squared is 4 times 2 is 8. And so it's 3 I0 over 8. And so 3/8 of the intensity of the original light here made it out here if this guy makes a 30-degree angle with the polarizer. So this is polarization by reflection, and I did a little demonstration of this earlier. But here it is, a light ray comes in, it of course gets reflected the way it normally does, angle of incidence equals the angle of reflection, but it gets partially absorbed, and we've seen that in a bunch of different demonstrations. And by the way, the surface that you're reflecting off doesn't have to be clear for this ray to get absorbed. Of course, it can be a black slate tabletop like I showed on our labs, or water, or glass, or anything. And so some of it's reflected, some of it's absorbed. The refracted ray, the absorbed ray, obeys Snell's law, and so we can say, in this picture, we can say N1 sine theta 1 is equal to N2 sine theta 2. It turns out that when the reflected ray, this ray, is 90 degrees to the refracted ray. So let me give you a different example, right? If the ray came in like this, then it would go out like this, and the refracted ray might be like this, something like that, right? These are less than 90 degrees apart. These are kind of more than 90 degrees apart, and it just depends on what your incident angle is to determine whether where the 90 degree point is between this ray and this ray, right? But when they do make a 90 degree angle, that means this guy's light is fully polarized in the plane of the reflecting surface. And that means if you were wearing glasses that were polarized perpendicular to that, you would wipe the glare completely out, as we kind of did in the demo we looked at earlier. And so we could say this. We can answer this question for two surfaces N1 and N2 in the following way. Since this angle and this angle are perpendicular, that means since this is 90 degrees, would be 90 degrees, these two would have to be 90 degrees. And so we could say theta 1 plus theta 2 equals 90 degrees at the polarizing angle. That's the angle where this occurs, where these two guys are making a 90 degree angle to each other, and we get fully polarized light. It's also called the Brewster's angle. And so what that means is theta 2 is equal to 90 degrees minus theta 1. And so I could rewrite that Snell's law at the top there. I could say N1 sine theta 1 is equal to N2 sine of 90 degrees minus theta 1. Right? I just replace N2 with that, theta 2 with that, and that gives me N1 sine theta 1 is equal to N2 cosine of theta 1. Because sine of 90 degrees minus theta is the same thing as cosine of theta. And I can combine those two, and I can say, look, tan theta 1 is equal to N2 over N1. Or I'll just start across here. At the polarizing angle, that angle is the inverse tangent of the ratio of the two indices of refraction. So let me just do another example here, so I can stop that one. I'm going to keep this picture going, and I'm going to say So what's the polarizing angle for light going from air into water? And so it was theta 1, but we might call it theta p equals tan inverse, because it's the polarizing angle of n2 over n1, and that's equal to tan inverse of 1.33, because that's the index of refraction for water, over 1. Theta p is equal to, so if I take the tangent inverse of that, I get 53.1 degrees. So what about air onto glass, where the index of refraction is 1.5? Then theta p is equal to tan inverse of 1.5 over 1, or about 56 degrees. We could do one more, and we could say right, and so this would be n1 and this would be n2, right? And then when I say theta is equal to tan inverse of 1.5 over 1.3, I'm going to calculate that one. I should have 2 3s there. .48 degrees. Okay, that's a little about polarization, and a little bit about the Brewster's angle, or the polarizing angle. Again, any angle is going to give you partial polarization. The Brewster's angle, or the polarizing angle, is the angle where you get complete polarization, fully polarization.